Well, thanks for having me. Like Michael said there, I'm a senior technical lead at Emeritus. We're an insurance company, dental insurance primarily, and based out of Lincoln, Nebraska. And I work on on one of the many team software teams we have here. The repo link is down here. It has the presentation as well as the demo code we'll show. Um, my Twitter handle is there, although really anymore I tweet about is why won't Major League Baseball resume play and other such annoyances of quarantine life, as well as random technical stuff when in between those periods of rage. All right, let's talk about web page speed. So, things people would never ever actually say, right? Like, I love autoplay videos. Man, just can't get enough of my phone just randomly barking out at 4,000 decibels some autoplay video when I'm browsing to some website, right? Like, I love ads. Who doesn't love ads? Ads definitely are destroying the fabric of our society through Facebook. So they're great. You know, Chrome sucking up 4 gig of RAM. As a matter of fact, if I pull up Chrome right now on my MacBook Pro, it's like 3.5 right now. One person's going to say that, probably a Slack developer. And this web page is just loads too fast. Nobody in the history of the world ever has complained about a web page loading very fast. So all these things are things people would never say, right? That's something we can attribute to just like sheer greed, right? Like reason autoplay videos exist is because ads, right? Reason targeted ads exist is because Google and Facebook don't become like $100 billion companies by accident. I have no excuse for Slack. I can only assume that they just like don't care. But web page speed. So why is web page speed so slow? Well, currently, despite 5G, this is my Pixel 3, which has more power than most computers did about 7 years ago, and dedicated engineering teams are some of the most advanced companies in the world. Most web pages still load like it's 2001. Barely any faster than dial-up, as a matter of fact. The average page speed, according to Google Web Surveys, which is basically like every Chrome device, unless you explicitly opt out of it, sends performance statistics back to Google. Average web page loads in 19 seconds in effing 2020, because that's just where we're at right now. So why is this so slow? A couple of different reasons, but what we're going to focus on is one, byte for byte, JavaScript is the most expensive thing you can ship to a browser. Literally nothing else. Images, HTML, CSS, way faster. JavaScript, very slow. So part of the reason we have to blame is our sites nowadays are extremely JavaScript heavy. Frameworks and all the rest. Also interactivity and all that type of stuff. Also, a lot of people, myself too, when I first started really getting involved in page speed back in 2017, we always saying like, well, my page is actually perfectly fast as long as you ignore all the other garbage that people throw on my page. Stuff like third-party tags, all these huge images, I don't know, like analytics frameworks. Now, normally this is when I ask for a raise of hands, but Babylon 5, which is literally the best TV show ever made, and I use literally correctly there. There's the Vorlons, it's like advanced race, and they have a saying, understanding is a three-edged sword, your side, their side, and the truth. So where we're actually arrive at after this is the understanding of somewhere in between those two things, right? You know, it's not all JavaScript's fault. It's not all third-party tags' faults. Why is the web so slow? Let's understand it. So to be able to do that, there's 3 steps we got to go through. One, we have to understand the architecture, right? How do browsers actually render pages, right? We have to be able to understand that so we can figure out how to improve it. We have to be able to measure the performance of our pages. And we have to understand then, once we understand the architecture, can measure performance, is where we can apply optimization patterns. Okay? All right. First thing, understand the architecture. How does a page actually get rendered on a stupid, on my amazing Pixel or my iPhone or whatever else I got in our hand? We usually talk about, when we're talking about page speed, the critical rendering path, which is the minimal set of steps a browser must take to render a web page, right? We're not talking about like stuff that gets pulled in later, deferred stuff, just the bare minimum before a user can go to your page and do whatever it is that your company sells or, information you're trying to present to them. So there's 4 steps to this. We have to construct an object model. We have to create a rendering tree. We have to layout, and we have to paint. So all those 4 steps are done, your people aren't seeing anything or being able to do anything. All right, constructing the object model. First step. This is a 2-part process. Okay. First part of this, we have to fetch and parse HTML and the CSS. Okay. Here is this source from Google. This is the lowest level part, right? We take bytes, we turn those bytes into characters. The browser takes those characters, turns them into tokens, then puts them into nodes, and then smushes those nodes into the DOM, document object model. Okay. It creates 2 object models actually. It creates HTML, the document object model for HTML, and CSS, the CSS object model. Does it for all the HTML and CSS on the page. So first things first, understand is obviously the more bytes, the more stuff you're shipping, the slower this is going to be. All right. So we've grabbed all the bytes, we've turned it into object models, we've smushed it all together for CSS, or we've constructed CSS object model, and we've constructed HTML object model. We now have to create the rendering tree, which is where we take these 2 separate things and we push them into one. So we take our DOM tree on one side, my amazing example of div class speed, and Martine, I am the world's worst CSS person, so I apologize in advance for the awfulness I'm on display. This is about the limit of my CSS skills. Okay, so we have our CSS object module and our DOM object model. What the rendering tree does is it pushes, it basically matches those, right? Starts at the top with HTML and goes through each div, looks in the CSS. If it finds that, then it applies it, constructs one big one. Something really important to note here, this only consists of visible elements. So as it goes through, if you're using, we'll get to these later, like CSS media queries, or even some of those div class, visible none, hidden, those it ignores. Just completely skips when it constructs the rendering tree. So we'll get to why that's a performance improvement later on. But you can think of any of that type of stuff. The browser, when it gets to this step, it's just going to ignore it and move on. So when it gets done, the rendering tree looks like this. Div class, it takes our HTML document object model, and now it has a CSS combined with every single part of the every single element and node in your document object model. Next step. Okay, we fetched all the CSS and all the HTML. We smushed them together in the rendering tree. Now the browser actually has to figure out where the heck to place it. Layout. So this determines the size and placement of every element on the page using the ever-loving box model that probably everybody's familiar with nowadays on the right-hand side. It does this by taking the render tree, retrieving device viewport. How many people have mindlessly set device viewport to whatever without really understanding what it did? That's what it does. The meta viewport, and it places every object on the page. So for each object, it constructs a box model, applies any CSS element, places it on the page. Okay. The last thing it does is it paints it. Actually renders the pixels onto the screen. We're not going to talk about this too much because in most modern browsers, and every modern browser, I believe even IE 11, which isn't modern, but it's still a browser we have to deal with until 2030 of the heat death of the universe. This makes use of the GPU, so it's extremely fast for almost all scenarios. This is usually in 10 milliseconds. If your page runner's time is 10 seconds, it's very small. Only usually an issue if you have to ever deal with very, very cheap Android devices on mobile, which have awful GPUs. But even then, it's rare. You have to care about it. All right. So 4 steps, right? Fetches the CSS and HTML across the network, takes all those bytes, turns them into characters, turns them into tokens, creates tags, smooshes them together in the rendering tree so the CSS and the HTML match, lays them out on the page, and then paints them. You might be asking yourself, what about JavaScript? Well, this is why JavaScript is one of the hardest things to optimize for. All right, there are 4 steps to run JavaScript once it's encountered. So as the browser is going through and constructing that render tree and parsing the HTML, whenever it encounters a script tag or inline JavaScript, it immediately pauses everything it does and runs these 4 steps. It downloads the JavaScript, right? With an exception we'll get to in a second. Parses it, compiles JITs it, and then executes it every single time. So let's think about that. Well, if you look at JavaScript execution, download is network bound, right? That's the speed of download is going to be the speed of your network. But parsing, compiling, and execution are all CPU bound. One of the things you'll discover if you ever have to optimize for Android devices and slow Android devices at that is that JavaScript's page speed execution is almost entirely CPU bound. But not just those. Like if I screenshot here, this evaluating script, it took 10 milliseconds just to compile the dumb thing, and then 257 milliseconds to execute it. That's a pretty big chunk of time. But not just, like I said, really slow Android devices. Let's take a look at Gmail. All right. So, drag this over. Everybody can see that, I believe. All right, here's my Gmail. Nothing terrible good. Only unread mail forwards from my mother, which is about right. Okay, so I'm presenting this on a it's a MacBook Pro. I don't know the specs. I'm not a big Mac guy. It's a good computer. Costs money. So we'll go over this in a bit, but Google has ways we can throttle. So right now I'm gig fiber. Let's throttle this down to fast 3G, which I believe in Google's terms is like 1 megabit download. So we're going to turn it to fast 3G, and we're just going to reload the page. Kind of see how fast it goes. Get my loading Gmail icon. It's not super fast, but a couple seconds it came up. It wasn't that awful. What about, it's still loading, but again, I can click on things. I can see my inbox. It more or less is there. What about, oh, I should have profiled it. That was a mistake. Hold on. What about if we do the other thing? So remember I said only one of those 4 steps for JavaScript was CPU bound, or was network bound. A lot of it was CPU bound. Let's turn my CPU throttling to 6x slowdown. So it's now executing 6 times slower, about what a medium performance, I hit reload, about what a medium performance Android device is. Sure is fast. Wow. So the difference in this, and I'm on gig fiber still, there's no network slowdown. All of this is, Gmail is an Angular app. I actually like Angular, by the way, before anybody throws something at me. But this is just CPU. This is just having to download and JIT and execute the JavaScript. Gig internet, I could be on the fastest 5G in the world. It's not going to go any faster than this. And this is Gmail, run by very competent professional engineers. Still, I can get to it now, but you can see how big the difference is, which is not typically what we think about, right? When we think about page speed, we kind of focus on download sizes, but JavaScript execution is very CPU bound. All right, let me go ahead. Still executing. Let me go ahead and exit that. We'll get to that. We'll go back to that example here in a little bit. All right. So keep that in mind. Is just like CSS, JavaScript is blocking that render until all 4 steps have been completed. So if your page is heavy with JavaScript, it has to do all those things until your people can actually view and interact with the site. And as you saw from Gmail, people with bad or low CPU devices, or not even just low CPU devices, you have to remember, a lot of corporate people are stuck with IE11 and 2 vCPU terrible Toshiba laptops with 4,000 antivirus scanners running and have 0 CPU, right? They are also effectively network or CPU bound because corporate IT is awful. So it's not just Androids, it's also everything. It's also your core users, or it could be. Okay. There are some caveats to these hard and fast 4 rules, though, because it's 2020. Some stuff, obviously when they first wrote these specs, they started this is unacceptable. Let's figure out ways to improve this. So there's, depending on what you put and where you put it as far as JavaScript, it will either block render or block network. You can take a look at this definitive source, which I sourced from a GitHub gist, which is made by a Google engineer, because that's the authoritative way of how stuff blocks in 2020. You can see like inline JS obviously blocks all the time. Async scripts don't. Script defer also doesn't. Script and head does. Script and body doesn't. It just kind of depends on where it's put. So there are techniques we can do to limit these. Although it's important to note that while script defer, script defer, script async won't block, as far as actual parsing, you'll get what Gmail had. You'll see a big loading icon because the whole app is still built around the JavaScript executing, pulling in network traffic, et cetera, et cetera. But important to know where you put JavaScript, what tags you put onto it, which we'll get to in a second, depends on if it's going to actually block the render or kind of execute later. Although depending on your page, if it's any faster to the user, really depends on how your page works. Okay, so JavaScript, super important, obviously, for page speed. Probably the most important things for most apps you're building. So how does JavaScript actually execute? How can we speed it up, more specifically? Let's start about JavaScript threading. Famously, JavaScript was made in like 9 days, right? Like one guy was given, he's like, here's 9 days, build me a script language, go for it. And unsurprisingly, the engineer tasked with this picked the easiest possible threading model because he wasn't an idiot and he wanted to focus on what was important. So he created JavaScript event loop. So everything in JavaScript is single threaded, with an exception we'll get to later. That single thread is called the event loop. Here's how the event loop works, right? It's consisted of kind of 3 different things. We have a stack, which is just your typical stack, right? Everything's popped onto it and then it iterates down through it. You have a queue, which is where the next set of messages are waiting to be processed. In JavaScript things, this would be events, promises, other function calls, set timeout, set interval, that type of stuff. And then last, you have the heap, which we don't usually give too much a crap about. Heap is just where we throw memory stuff on the memory. Unless you're iterating through really gigantic blocks like JSON data or something, you don't typically have to care about the heap. Slack developers obviously don't, so it works. Who cares? So this all looks good, but one of the things it helps kind of visualize it. So let's take a look at some kind of fake-ish code, which I still need to update the screenshot from KCDC. Oh my goodness. Ignore this. Ignore this shame. This shame. I forgot to update it for you guys. I'm sorry. All right. So if you look at this JavaScript code, what the stack would look like in this case would be bottom-up representation, right? So if you think about this, it calls start me up. Function start me up ends up calling doing thing. Doing thing ends up calling me. Well, the stack, when this event loop executes, will be that order reversed, right? Calling me, doing a thing, start me up. It executes 1, 2, 3. And executes until completion. At which point it would process the next thing that was waiting in the queue. I found when understanding the event loop, one of the easiest things to do was to write it out in JavaScript and to actually write a real event loop implementation of JavaScript, which is stolen from, you can actually look at, obviously, Chrome source code, and basically their C++ event loop implementation. It's way more complex than this, but the base implementation is the same. And Firefox and the rest are the same, too. This is actually, the event loop is a spec. It's part of HTML spec. So all modern browsers implement the same way. So if we were going to build an implementation, right, this is what, on the left-hand side, what our loop would look like. It would take in messages from the queue, and then it would wait for messages and execute loop over them, right? If they were there, it would pop them off, call the function, and just keep doing that until it ran out of messages. Here's a list of messages, right? Function. Here's just a bunch of functions we pass to it. The exact same as the one. It would just start at the top and go down, 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 and keep going until it's complete. So single thread, everything runs, waits for the next one to go, then starts, keeps going until there's nothing left. So if you think about this, JavaScript is very important. You only have to do one thing at a time. But obviously, if we could only do one thing at a time in JavaScript, and we had to do all these network requests and all the rest, we could never do anything, which is where the queue comes in, right? Again, they were not complete idiots when they made JavaScript, or the event loop for that matter. So they recognize that if I'm fetching I/O, I don't want to block the browser from being responsive. So we had to create a way of handling those long-running input-output tasks. So the queue handles non-blocking code. Specifically, handles stuff like set timeout, set interval, event handlers, almost every I/O related thing, although we'll get to the one exception of that. The queue is not part of the event loop spec technically. The different implementations are part of other specs, but every browser works the same. So if you ever wondered, famously when I was first getting introduced to JavaScript when I was a newbie, it's like set timeout would fix all the problems. A lot of times the reason set timeout fixes all your problems is because it waits for something to get done in the stack and then it executes later. So something with blocking, set timeout runs, something the code is ready and it can handle. So let's consider the queue. It's a quiz. It's a great quiz. If you take a look at this program, which is real JavaScript, we'll execute here in a second. If you look at the console logs, just give yourself a few seconds. What order do you think they get printed out in? So, right? So we have console log, we start. We set up a onload, we set up a new XML HTTP request, an event handler that on load end, it'll just write non-blocking complete. Excuse me. We have an open, a send, and an out of try block. And then we have an error, which, spoiler, won't get executed, and then a finally, right? Finally, that's done. In a traditional programming language, I can tell you how to be executed, but how in JavaScript, keep in mind how the queue works, right? And how the stack works. I'll take a look. So, here's our code. Here's our code again that we're going to be executing, right? Starting our program, nothing special. All right. Well, that's weird. So,
nice.
Take a look there. Now, why does it do that? It's still, by the way, it will eventually return. My corporate proxy is busy hating on that JSON placeholder, but it will eventually show up. So let's think of why this is. So remember the stack, remember the queue. So the first thing it does is the stack says, okay, we're going to console log starting our program. There it goes, non-blocking complete finally. But then we're going to have an event handler. Specifically on load, we're going to call non-blocking complete. Well, remember, every event handler is pushed onto the queue, which means from this point on, it's going to run this entire program start to bottom before it ever processes any event handler. If I had a set timeout in here, it had the same effect. That also won't get shown up. So this is you're gonna exit the finally, like nothing else supersedes that. Finally is gonna execute. When this entire program is done, then it'll be able to process the next thing in the queue, which because it's a very simple program, will be the onload end, non-blocking complete. So control flow in JavaScript and how stuff works is quite a bit different, right? In other languages, if you're a Java or a C# programmer, like you would expect finally to always be the last thing, but it's just not the case in JavaScript. Every event handler is pushed onto the queue, and the code in the stack is going to run to completion. So this will always execute later. All right. So blocking, non-blocking I/O. So this was an example of this right here was an example of running again non-blocking, right? We ran, everything worked just fine. Well, there is one way in JavaScript to execute a blocking method. So if you ever done this before, hopefully never, you'll see, I'm going to scroll over a little bit. There is a third overload on request open where you can specify, actually don't run this async, which if you do that, is about the only way in JavaScript you can actually block the browser. There he goes. You can actually block the browser from executing. So this won't get tossed on the stack. This will execute one all the way from the top to the bottom, because in this case, we're blocking this. Keep in mind, this is Node. It's a very simple example. If we had done this, for instance, in the browser, this would actually lock the browser up. And if you've ever seen a browser saying, hey, can't respond, waiting for something, this is what's happening. If something is locking that main thread, well, one of the things that could be happening, something is locking that main thread as it tries to retrieve retrieve a second resource. Similarly, I can also do non-blocking, which is the exact same thing. It just goes through. It doesn't lock my computer up. The stupid thing's going too fast. It's hard to show. I should have turned my network down. Usually I'm at a conference on terrible conference Wi-Fi, so it's really easy to demo while pulling in a 100 megabyte PDF. It takes too long. But when I'm on my home gigabyte, anyway, who would have known? This actually takes quite a bit longer and pauses. This does not. And the only difference is, again, the request open there. All right. So, quick review, what we've learned. Render tree, right? Downloads CSS, downloads HTML, pushes them together in the render tree, computes the layout, figures out where they lie, and then paints it to the screen. JavaScript. When a browser encounters JavaScript, it pauses, has to do a couple things, has to download it, has to parse it, has to compile it, has to execute it before it can proceed on those other 4 steps. And all of JavaScript is executed as an event loop, which all means there's a single thread, it does something, everything in that thread. If you make I/O or event handlers, then those are queued and processed later. Okay, that is the sum total, well, the 20-minute version of how JavaScript execution works. So let's talk about measuring performance. All right, Chrome and Firefox both ship with pretty good performance monitoring tools. Actually, Edge does now and before as well. Same thing. They kind of, for the most part, is what day-to-day I use for performance monitoring, right? So let's take a look. Let's go back to our Gmail scenario. Wherever I find my okay, I don't have a Gmail window. I'm going to create a new one. All right, so let's go back to our Gmail scenario. Let's take a look at some performance here. All right, so pretty easily here. You just go Performance tab in Developer Tools. I'm going to zoom in a little bit because this can be a little bit small. We're going to reload it and start profiling. Okay, good. Want to make sure I wasn't throttling. All right. Just go ahead and stop profiling because I'm going to wait for the full page load, and we can take a look at what it's doing behind the scenes. This usually only takes a second, but of course, important to note, this is one of those things that if you have a slow computer, it'll really kill you. Okay, so here's what it looks like. Got a whole lot of information. I'm going to zoom in. We're going to start from the top, or start from the top. Okay, so up here at the very top, we have a list of what the browser was doing as far as its threads. So here it's downloading. So I'm sorry, orange is I/O. This purple is CPU. Okay. It also goes ahead and creates screenshots for us. So as I mouse over each of these, see loading Gmail. I can expand the timeline out. You can see as it changes, it goes ahead and creates screenshots. Pretty cool. Down here, I'm going to zoom back out so I can drag this over. Down here are the different threads, threads or tasks, like what Chrome was actually doing. So you have the network, just shows what it was doing. Here it's, I don't even know, running a bunch of fetches. Yeah, just grabbing images. And if you mouse over individual stuff in here, you can see what exactly it's grabbing. This is grabbing some mail data, I guess. Okay, network thread. Frames just showing what animation is running. Interactions, if I was actually clicking or doing that type of stuff, you'd see that. But in this case, what it's actually showing is all the different Gmail animations. It's the loading icon, loading Gmail. All right, all that is pretty cool. But where I tend to focus most of my stuff, and probably you will too, is under timings and main. So main is the event loop. Okay. Timings. I zoomed out too far. There we go. When you zoom in too much, there we go. All right, timings. So we'll talk about these in a second. These are the built-in paints events that the browser has. DOM content loaded, which probably most of you have heard before. First contentful paint and first paint. So these are built in, and Chrome will put them for you right here on the side. Also under here, you'll see under main, you'll see exactly what the program is doing. So specifically what, this is all the JavaScript, right? It's telling you here you can see this is minified code, but you can see exactly what it's running. This looks like Google Hangouts, actually. Yeah, this is Google Hangouts, right? So Google Hangouts, this entire thing, removing child, all the rest, took almost a full second. Here you can see where the browser's parsing HTML. Basically, what I'm trying to show is it gives you extremely detailed of exactly what's happening and exactly how long each function call takes. And it drills all the way down. You keep scrolling down and you see everything, right? Also here it shows, I mentioned not most stuff is very quick GPU, but here you can see the GPU statistics, all that type of stuff. More importantly, though, you also have, scroll back out. If I scroll back to the main, it gives you the full list of how long everything takes. So this is what I mentioned at the start. Remember we said JavaScript is the most usually performance heavy stuff, and especially on Gmail. Well, look at the scripting. The 10 seconds I let for this thing to run, almost 7 seconds. 7 seconds was just waiting on JavaScript. About a second and a half was waiting on rendering, which is more or less the smooshing the CSS and the document object model, and 209 milliseconds is loading, which is more or less just waiting on network traffic. Which is unsurprising. I'm on gig fiber. And then a small fraction of the time, 113 milliseconds, was waiting on Paint. That just is GPU, right? So very, very little of it. And here you can see, if you go bottom up, you can see exactly how long everything took. Here's JavaScript. It'll break out everything. You can see the different 7.4% was whatever this clear timeout function was. And you can kind of drill in more, too, on your own page. Pretty cool. Call tree, all that type of stuff is showing up here. You can also get to some of this later stuff here. You can see where different events happen, send requests, like Paint, exactly how long it takes, recalculate styles, which is why that's a terrible idea in a second. All right, ton of information here. There's even more too I didn't go into. There's all this compositor, meteor, all that type of stuff, which for the most part we don't have to worry about, or are niche things like you're building a video site or something like that, as well as service workers. Okay. An absolute ton of information there. However, something to keep in mind, that is from my pretty optimized MacBook. What about real users? It's important that when you look at something like that, again, it's from my MacBook, which is a pretty powerful device. I can hook up my cell phone, but usually most developers I know are using the latest gen iPhone or the latest gen Pixel. They're not using what most customers use, which is usually a couple-year-old device, right? So we're so used to having the best, or I'm like, if I take a picture of my home desktop, I'm Google profiling on my 16 fucking core Xeon here, right? Anyway, it's important to have real user monitoring, what real users happen. So a couple different ways of doing this. You want to capture stats on not just a wide array of devices, countries, regions, depending on how active you are, network conditions. In Nebraska, and I'm probably the same in Indiana, to be honest, you have a lot of rural customers. If you're targeting people, there might be on really unoptimal or unoptimized devices. So you want to make sure, like, hey, does our page behave really terrible in rural areas of the country? So there's third-party paid tools available. T-Leaf, New Relic, Dynatrace, those cost some money. There's also ways, though, that you can utilize Google Analytics or other free analytics tools to send your own events, though. And we'll get to those in a second. But it is important to keep in mind that when we measure performance with these awesome tools here, we'll also need some real user monitoring as well to find out what the conditions are with real people. One of the most startling things that is scary with real user monitoring is I was doing work for a big cell phone company that just merged with another big cell phone company, and was discovering that parts of the page were 2 or 3 times slower on Androids. Like everybody was browsing and going through the upgrade experience on their iPhones, because a lot of people have iPhones, or on my case, on my Pixel. And then we looked at when we got real user monitor set up, we noticed that it was taking like 2 or 3 times as long as Androids. It's because the Androids, just the CPU was so bad. Anyway, I fixed it, we fixed it eventually. But it's that type of insights. You'd have no idea. Even the best QA didn't detect it because nobody was trying it on these terrible Android devices. These very like $50, $100, cheapo specials that people buy, or just have laying around. I don't know about you folks, but like I have nephews and nieces, and kids always get like the 4th generation hand-me-down broken crack screen Androids. So you have to keep that in mind too if you're designing stuff for kids or teenagers or whatever, and they're not using the latest devices as well. It's important to have real user monitoring. All right, so with all this measuring of performance, there's a couple of built-in events we want to take a look at. These are part of the spec. You can look up their definitions on W3C if you really care. So DOM interactive, excuse me. This is when the browser has finished parsing the document. Think about that a render tree completion and painting. That's what DOM interactive is. Does not necessarily mean your page is usable. It just means when the browser has finished parsing the document. DOM content loaded means that the browser has finished parsing the document. So we've constructed the DOM, smushed together CSS object model, and scripts that have been marked as defer and inline have finished executing. Again, if I go back, I'm going to real quick exit out of this. We'll go back to here, right? As I mentioned, Google actually shows us these timings for us. So DOM content loaded for Gmail was 3 seconds. This is the screenshot of what my Gmail looked like at 3 seconds. Like nothing, because most of Google scripts are async. They're pulling it from behind, they're executing. So DOM content loaded, depending on your site, and if you have a heavy SPA site, is usually not very relevant. I mean, the site didn't really become usable until 7 seconds when I started seeing my messages, which is almost double the time from DOM content loaded. All right, let's go back to some of these. Just want to show how, if you're just reporting on some of these, they're oftentimes not super helpful. DOM complete is exactly what it means. That is everything has run. Literally everything, ads, analytics, third-party tags, everything possible has finished, and the browser has had a single network traffic request. First paint. First paint is probably what you think it is. It is the first time. So if I type in www.google.com and hit enter from another website, first paint is when it transitions from the other website I was on to a blank white page. First paint is really a measure of how quick network traffic is, how fast your servers are responding. It doesn't actually mean anything is actually displayed that's useful to the user. First contentful paint, on the other hand, means that the first time that after typing www.google.com, anything at all from google.com is rendered on my screen, whether it be the image or a headline or whatever. It doesn't matter, anything at all. Okay? So there's the built-in events. And again, the biggest problem with these is that on modern, non-trivial websites that have a lot of JavaScript, they're just not that useful. Some of them are, again, like first paint. The first contentful paint could be a good indication of having server issues or network problems, But DOM complete, I've shown that Gmail thing, it just doesn't show us anything. Like it says DOM complete, but the user can't do anything. And that's the case on almost every modern site I go to with a heavy amount of like React or Angular or whatever framework you want to pick on it. Luckily enough, a couple years ago, they created a bunch of performance APIs for us to use and for us to dig into. So here are all the different ones. The ones with window.performance API is the legacy ones. Navigation timing, this is kind of where, again, that load event and DOM interactive, all that type of stuff comes from. And you can find it on that namespace if you take a look at. User time is what we're going to get to in a second. Those are ones, high resolution APIs that we can use for our own custom events. We'll get to why that's so powerful here in just 1 second. Resource timing. This is like, if you ever want to know, excuse me, how long exactly it took to request and fetch a resource. And I mean exactly. It's going to show you how long SSL connection teardown took, DNS resolution, byte fetch end. Every one of those will be captured for every single resource you have. So if you're pulling in, like oftentimes, I call this the API shaming kind of API, because like if you have to call like a third-party API team, they're like, oh, it's up super fast. And you're like, actually, no, it's not. Here's exactly how long it took. Anyway, that's it. Not that you should do that or have to, but sometimes you have to. And the last is the timeline, which is just like a performance observer. So this is what is the third-party tools, including ones you can make yourself use. You basically, it's an observer pattern, right? You watch a namespace, you grab the events that come through, and you post it off to an analytics site or something like that. Just performance observers. Okay, let's take a look at so we're taking a look at this one, the user timing. Okay, so as we saw here, the browser has this, or the content monitoring tools will actually display these for you. So here's an example using the user one. Oops. Pretty easy. Here are the steps. You create a mark, your start mark. You do some work, and then you create an end mark. So start, doing some work, end. Then you add a measure, which just measures the time between those two marks. It'll measure them to like, I think the 100 nanosecond. It's extremely fine grained. Those timings will display for you in Chrome DevTools. So here's an example. This const register performance up here at the top left, creating an end and then giving a callback that when the function's done, it can just call the result, which will add a mark, measure them, and log out the performance. Oops. If you do that, what you get in Chrome DevTools is this awesome stuff here. You can see our mark. So this, instead of this stuff down here in the main, which is, it's like a lot of minified JavaScript, run micro tasks. I don't really know what this is doing. Well, if I do this, I can say exactly what it's doing. It's just whatever I call it. This function measure network work async true. There, exactly how long it took. I can look at my code and see exactly what it's supposed to be doing. It's amazing. You can then also use it to report to your favorite analytics service, right? Broadcast, hey, cool. Every user, you can broadcast these exact events to your analytics service and get really fine-grained real user monitoring, right? So you say measure network async true, send to Google Analytics, then you can see how long it took on Androids and iPhones and geographic area, whatever other stuff or whatever analytics tool you use. So that's cool for demo, but what about a real site? I happen to know a real site that uses these. Just off the top of my head, no reason. All right. Unsurprisingly, a cell phone company cares a whole lot about how fast their site is. This is going to shock you. So let's take a look at what these performance measures look like. So I'm going to go to the Sprint phone wall. It's what somebody calls the phone wall. I'm kidding. They don't care if I talk about it. All right. I'm going to reload the page and connect a performance trace using Chrome DevTools. I'm probably going to wait for the entire thing to load because I'm lazy. All right. There it goes. Let's give it just a second as Chrome DevTools finish here. All right, so let's take a look at what I did. So we're going to zoom in here under timings. So what we did on this side is we organized components into 3 different buckets: high priority, medium priority, and low priority buckets. We create performance measures around those. So you can see here that all of my JavaScript took 253 milliseconds to run for high components. And if I dig in even more, hold on, I'm going to zoom in a little bit. I can see the different subtasks that took long part of this, right? Each under high components, I have an init nav, I have a header, I have a intention modal. Similarly, under medium components, I'm going to zoom in again. I'm going to zoom out. I have all this. So medium components took about 55 milliseconds, and here are all the different stuff it takes. These are all the different components that it's loading. Black box, header, log on. Here's exactly how long they take too, 201.5 milliseconds. And then directly underneath them, let me zoom in. So getting this right on a second monitor is interesting. I'll put it that way. It's a little bit easier when you're on a, there it goes. So then directly underneath them, so you can see, okay, cool, cart item count took 10 milliseconds. Well, maybe I'm really mad about those 10 milliseconds. Well, directly underneath it, you can see exactly what's taking the time. And scroll down here. Here's all the different functions it's running. So for whatever reason, this function took 7 milliseconds. And this took 1.0 RxJS. Took 1 millisecond. And subscribe took this. So you can optimize based on the results. And you know exactly what function it is. Similarly, you can do that for any of the rest of these, right? This black box, actually I know what this is. Black box took 11 milliseconds. Well, here's the different stuff it does, and here's exactly how long it took, and how I can then optimize based on those function and method calls. And it's real time, and it's real for my user. And again, if I report those back to Google Analytics or whatever analytics framework the site is using, we can then see, hey guys, for some reason, header log on is taking too long to finish. Anu should go fix it or whatever. There's all sorts of stuff we can do. It's really easy for me to just look at performance tools and see exactly how long everything took to load. Really takes the mystery out of what's taking so long. Hearts really helps us understand what's going on. So you can also do the same stuff for like Angular, right? So let's take a look. I believe Mr. Dowden here has actually did this for me to make this a decorator, so you don't even have to do this much. But in theory, so you could just add an Angular you could add the performance mark and start. So on ng on init, you'd add the start mark, and on after view init, you'd add the end mark, right? So every single Angular component, you know exactly how long it takes to instrument. It would show up right for you if you just did that two stuff. What about React, right? React similarly is very simple. You could add a start, and then under render add a start, right? And on a component did mount and end mark and a measure between them, and then you can see exactly how long every one of your React components took to execute. It's pretty amazing stuff. It really lets you see exactly how long every component does, and lets you invest your time into, hey, this component's taking too long, or this one's going, whatever. You don't have to like dig through a ton of source code to figure out what's going on. It's just right there and shows up for you. All right. So a couple other tools. Talk about web page tests. One of my favorite. It's an open source one that supports user-focused performance metrics. There's a nice website that's available, webpagetest.org. You can also download standalone Docker containers if you want to play around with it in your CI/CD pipelines. It lets you run a bunch of different tests, capture nice data from all across the world, different browsers, even different devices. It's pretty sweet. It's really nice to instrument up and be like, hey, why is this page taking so long on the East Coast on iPhones? Well, they have an East Coast data center. I can run an iPhone. I get the full performance trace mark and see exactly what's going on. Again, if you use Docker containers, you can also integrate into your CI/CD pipeline to do performance tests, or just report performance for every build, which is what I usually end up doing. So last thing about measuring performance I want to talk about is the rail model. We usually, in this talk, I've been talking a lot about just one thing, rendering, right? How fast can the user see? But there's three other things in load. There's two other things we want to talk about, animations and idle, okay? You got to think about all four when you consider the performance of your site. So animation, maybe your site doesn't have any animation. It's not that big of a deal. But it's something to keep in mind if you use heavy animation. I've seen some really bad animation written like JavaScript that just destroys anything that's not like some ridiculously overpowered machine. I've also seen some really elegantly written CSS-style animations that'll work on everything, even the worst-powered CSS or worst terrible $100 Android. So you got to think of how this browser behaves in all four scenarios. Similarly, I always tell the story. I've seen idle take down a company's call centers before. One of my favorite stories. So we had a site. There was Citrix, which is probably most of you are familiar with. It's like a remote desktop technology for Microsoft. You Citrix in, whatever. It's a remote desktop tech. It's used by enterprises a lot. This particular company, all their call center employees, some work from home, some work from the call centers, but they all use Citrix to log in to like pull up the web browser, the company intranet, and do all their call center-y things. One of the things they did is they often brought up the website and just let it sit there in a tab or a couple tabs, and they let it idle. Well, somebody injected some code, a third-party analytics, that was then pegging the CPU because every like 30 seconds. Okay, problematic. More problematic when you consider Citrix is like a shared thing. So you had hundreds of these desktops, thousands of tabs, and it saturated the CPU on all these servers. And they couldn't get any work done, and nobody could figure it out. We eventually did too. We eventually figured it out. But that's one example. Another example where idle can really kill you is battery performance on phones. Another client I was working with, we just happened to notice that the phone battery got bad when we were testing the site out. And we eventually discovered that there was too big of an idle loop running, and it was just sucking up all the performance, and including battery performance. Also on modern phones, they also start doing a lot of bad stuff to your website to try to prevent that, like throttling it, making it appear a lot slower than it is. So keep in mind, not just rendering and load, you also got to think of animation and idle to really test all those scenarios. Like just bring up your site, let it idle a performance and see if it's doing anything or sucking up CPU. All right. We talked about how the architecture works, how to measure it. Talk about how to optimize. All right. So once you've measured, one of the most important things is establish performance budget. There's performancebudget.io, which is my favorite one, which lets you say, get everybody as part of your website, say, hey, we want this thing to load in 5 seconds for 4G LTE iPhones. Everybody gets a slice. Here's exactly how long you have. Performance budgets lets you keep yourselves accountable and lets you understand what is possible and is not. I cannot count the number of times they've said, we want this page loaded in 4 seconds. I'm like, cool, here's what the page can do, and here's that pretty image you can't have. And then all of a sudden that 4 seconds became 5 seconds. Anyway, so establish performance budget, and then one of the first things you can do is just take a look, are your file sizes too large, or is render performance, CPU usage the issue? Just kind of easily take a look at, based on what you know about measuring, what is the most likely thing. So chances are you're going to run into the problem with your file sizes too large or just CPU. So Webpack has got a couple built-in methods of dealing with this type of stuff. Code splitting, right? One of the biggest problems, you think about that, going all the way back to the first thing we talked about, JavaScript, right? It has to download the JavaScript, has to parse it, has to JIT it, has to execute it. Well, if you just ship everything as one gigantic file of code, it has to do that entire thing, even if only 10% of the code applies to that page. So try to split your code out. Maybe have only the checkout JS load with the checkout, right? Or this JS load with different parts of the site. I use minification, right? Uglify usually just reduces the size of JavaScript by shortening variable names. Pretty common, but I, to this day, still see a lot of websites that don't minify their JavaScript. Tree shaking. I mean, how many people can say with confidence that every function and all their JavaScript or TypeScript is used 100% of the time? But I mean, I can't. Tree shaking is an automated way of finding and removing unused code, dead code. Again, the stuff you don't ship to the browser is stuff it doesn't have to download, parse, JIT, execute. Webpack Stats, such as a built-in plugin, it's an amazing thing to visualize exactly what you're shipping with your JavaScript and what is taking all that space. And it doesn't even matter if the code isn't being executed; it still has to parse it and JIT it. This is usually a really fun one when you first do it to see how much you're shipping for like polyfills, like Core ES6 and that type of stuff. It tends to take up quite a bit of space you don't realize. So Webpack has got some pretty good built-in ones. So about CSS. Remember at the very start we said that if the browser only cares when it constructs the render tree and layout of visible stuff and elements that are visible. So you can oftentimes use media queries in CSS to limit what the browser is, what is visible and what it has to parse for that page, right? Here I can say this only applies if if the minimum width is 768 pixel. So if for whatever reason it's bigger than that, smaller than that, it's going to ignore this style entirely. Media queries is a very advanced well, that's not very advanced. There's a lot to dig into here. I believe Martine actually has some talks that go into media queries. But the key thing to mind is if you media query match your entire or as much of your CSS as possible, it really limits what the browser has to parse and when it constructs that render tree and layout model. So especially if like most people, your mobile and desktop layout styles are very differently. Like if you can remove 30% of your CSS from ever needing to be parsed and smushed in together, it's a pretty big performance impact. Reflow. All right, Reflow is really bad. Reflow is anything that forces that browser to recalculate the layout of the page. Okay, so remember, downloads, render tree layout. Reflow starts back at render tree layout. There's a lot that actually causes this to happen. For instance, setting inner height, setting inner text, setting focus, scrolling, even just looking at window height, all of those cause a reflow. The browser has to go through and re-execute your entire page, which is like a couple hundred milliseconds. As a matter of fact, the thing I referred to before, that idle thing that took down a whole call center, it was actually because something was checking the window inner height every 10 milliseconds. Is what was actually causing the problem. Because they were just trying to see what there's like an analytics script, like what size of the browser is it in. So all of these, you also see them in the Chrome with dev tools. You'll see this scroll show up in the console log. Chrome is trying to tell you, like, hey, don't do this. It took 44 milliseconds. It takes a long time. Most pages I see dozens or hundreds of times. And people don't realize how big a performance impact it is. This GitHub gist right here has the full list of everything that forces a reflow. But the most common ones I see, again, are inner height, inner text, and window height, which people use window height all the time. Like window height, go mobile, do this. Or window height, do desktop this. Don't use that. That forces a reflow, slows the browser down, pegs CPU. Instead, you can use window match media, which is an amazing new API. Not new. It's available in almost everything, including IE11, which lets you pass in a CSS media query, which does not cause a reflow and executes way faster. Anyway, reflow, super terrible. Please avoid it. Network optimization stuff. End of the day, you still have to fetch a lot of stuff across the internet. So some stuff, use HTTP2, always requires HTTPS, and somewhat more modern web servers. It is now officially available on Windows with the latest IIS, and it's available on Nginx and Apache, among the most common ones. Turn on gzip. Natively gzips all the files, so like instead of shipping the gigantic block of HTML, it gzips it, strips away all that white space, or JavaScript for that matter. Use a content delivery network. Popular ones are like CloudFront, Akamai, Azure CDN. I can't remember AWS calls theirs, probably like Route 44, Purple Jelly Bean or something, knowing AWS. But anyway, just a CDN, it spreads your stuff all across the world, really reduces load. When designing high-performance websites, we usually rely on CDNs. At least I rely on CDNs to handle 99.9% of the traffic. Like, I'm not handling World Cup traffic without a content delivery network. But also, even if you're not handling World Cup traffic and you just want your users in Florida not to have to pull a web server in Seattle, like CDNs help reduce that literal light speed delay. E-tags, which is a whole specification around hashing content, and it lets the browser cache it locally and then check with the server to see if it's changed before it has to re-download something. It's great. It's amazing performance saving. Cache control, which is more the old school way of doing it, just allows on-disk caching by the browser itself. And time to first byte, which is a long delay time, indicates overwhelmed servers, maybe some misconfigured, any sort of random stuff going on. And last, cookies. Stop using cookies for everything. HTTP cookies get sent with every single request. HTTP2 has a very fancy way of handling this, where the first connection will only have all the cookies, and every subsequent connection won't unless you add a new one. Even so, cookies suck up a lot of bandwidth. One of the things we did when I was doing some performance optimization was discover that every single request was sending 12 kilobytes of cookies until we switched to HTTP2 and did a bunch of optimization. But that is actually really common. And again, it comes unless you're using HTTP2, it's coming with every single request. We talked about JavaScript is an event loop, it's single-threaded. There are some exceptions to that, 2 of them specifically. There's service workers. Service workers are separate threads that you can do for like offline caching, prefetch, but they don't block the UI thread. I almost always use service workers in the fact that I use them for prefetching and caching of network requests for my APIs. That way, when the main thread gets to them, the stuff's already there and it can immediately execute. Web workers are a little different. They're for high CPU usage scenarios. So the most common way I've used them is if I have to parse like a gigantic JSON payload, because it's a separate thread. So instead of parsing like 3 megabytes of JSON in the main thread, which will suck up a lot of CPU, I push it on the web worker. But there's a lot of scenarios for web workers. If you're doing like any sort of animation or games, web workers are used a lot to avoid locking the main thread and pushing CPU work off to another thread. But you can keep in mind, service workers, I/O, web workers, CPU. All right. However, all these are collected. There's a huge list of these. I collected them all for you. Excuse me. You can take a look at it here. It's got a massive list and linking to wherever I can the best practices documentation, because most of this was just years of working on it and pulling from best practices from various people. So all that's collected. You can take a look at it. There's literally hundreds of these. Other resources for you besides that. The cost of JavaScript from the Google V8 developer blog will probably open your eyes quite a bit. It's where they talk about how long every page takes to load, just how terrible most JavaScript is nowadays. Nice, again, critical rendering path, what causes the reflow, how scripts get scheduled. It goes on and on and on. Jonathan Mills, who's another speaker friend of all of ours, he has a good talk on service workers. You can take a look at there. A couple of folks who have done talks on web workers and service workers as well. And as always, the full notes and all of this, and including the slides, are available on the GitHub repo, as well as the demo code I showed you.